Hello and welcome to the fourth video in this series. Today I'm going to show you how you can create a NetCDF file using xarray in Python. I'll show you first how to put all of the data into the NetCDF file, and I'll include examples for one-dimensional data, two-dimensional and three-dimensional data. And then I'll show you how to add both global and variable attributes to the file. And throughout all of this, I'll show you how to make sure that your file is compliant with the climate and forecast conventions to make it a CF-NetCDF file, as well as the Attribute Convention for Data Discovery, or ACDD for short. If you want your file to be compliant with the FAIR data management principles, you need to make sure that you're following these conventions. A NetCDF file by itself is not necessarily FAIR compliant. Then at the end of the video, we'll run our file through a compliance checker to make sure it is actually compliant with these conventions. We're going to take this slowly and build it up step by step, but there are checkpoints in the description so you can skip through to whichever part is relevant to you if it's too slow. So let's start by initializing our dataset. We're going to call it xrds, and we can do that with just xr, which is the xarray module we've loaded in here, dot dataset. And we'll just quickly have a look at that in our terminal. And what you can see down here now is the xarray object. You can see already that there are specific places for your dimensions and your variables. And if you're doing this script in Jupyter Notebook, for example, you might also see that there's spaces for your attributes as well, and your variables are broken down between coordinate variables and data variables. I'm going to do something else up here now. Imagine we have a variable called depths, where we have some values, maybe 10, 20, 30, 40, something like this. Then when we initialize our dataset, we can add depth as a coordinate variable. So we go coords equals, we can open up a dictionary. We're going to call that coordinate variable depth, and we're going to make it equal to this depths variable that we've created here. If we print that, in the terminal below now, you can see our xarray object now has one dimension, depth, with a value of 5. This is the number of depth points. And we have a coordinate variable which has the values. And these have been set as integers by default. Then we can have multiple dimensions. Let's say we have latitude equals 78, 79, 80. Maybe longitude as well. And let's add those into our xarray dataset. We can just add more key value pairs. So latitude, latitude, longitude, longitude. Depth can also be pressure if that makes more sense for your data. But we should also talk about time. So let me create a quick array of timestamps. We can give our start equals, we need another library for this. Let's import numpy as np. np.datetime 64. And we can give it some time. We have our end time, which is going to be start plus np.time delta 64. And 24, that's going to be 24 hours after. So create a start time and an end time that's 24 hours after that. Then let's make an array of values called timestamp, which is a numpy array, and a range between start, end, and the increment is going to be np.time delta 64, 1 hour. I've made a typo here. I'm going to comment all of this out, and we're going to have a look at the timestamps. Here we go. So you might imagine that you can then just go add this in and add time here, timestamps. And you can see we have a time coordinate variable with a type of date time, and our values have been recorded here. Now you will see data stored like this quite often, but if you want to make your data compliant with the climate and forecast conventions, there's actually a different way of storing the time. And that is, instead of storing the values like this in timestamps, you instead have some array like time equals 1, 2, 3, 4, 5. And then you would have some units, which would be something like, in this case, hours since, and then you can just copy this start time. And then these units will of course be stored in the metadata. I'll show you how to do that later when we move on to the metadata. So we're going to add this here. And your time are integers. So you can have decimals if you want to indicate half an hour, for example. That's absolutely fine. And then you can just edit these units to indicate whatever level of precision you like. So you can have days since, seconds since, whatever. So why do we bother doing this? Well, firstly, it's to do with storage space. If you have to write out a long timestamp for every single instance, this can soon build up if you have a very long time series of data. This way you can use relatively simple numbers and indicate the level of precision here. And the beauty of this approach, being standardized, is that many softwares now know how to read and understand this. If you have a time variable with a variable attribute of units that is in this format, most softwares are now able to read this, and when you export some data from a NetCDF file, the times will often be converted back to timestamps for you. There's a good example on this page here, a brief history of NetCDF time, that will give you an explanation of why we store data like this, and I'll put a link down to this in the description. However, I do understand that often you have your data in timestamps, so the question becomes, how can you convert these timestamps into a list of either integers or floats that you can store easily into your NetCDF file? So we can calculate that. We're going to create an object called seconds since start equals timestamps minus start. So this will create a list where each value is the number of seconds since the start time. And I want this to be in as type int if we're sure that we have only integers, or we could use a float if we have some decimal numbers. So let's just print that. And I'm going to comment all this out again and run it. We see our values like this. One question you might ask is, what is the best practice for precision? So seconds is absolutely fine. Days is also fine. I would avoid using weeks and months, just because there can be some ambiguity in what time you're referring to because of differences in calendars. But I would say best practice is probably to use seconds, days, and perhaps years if you have years. The other question you might have is what to use as your start time. In this case, I've just chosen the start time of my time series. But another time that you might want to use is Unix time, which is the number of seconds that have elapsed since midnight on the 1st of January 1970. But I have seen some cases where people have been trying to concatenate data from multiple files, and this at least is easier if the start time is consistent between files. So let's update our xarray object now. Instead of printing this here, we could put time as seconds since start. If you did want to do hours since start, for example, to go back to what you have, you can just change, obviously, the name of a variable, and you can put as type time delta 64 and then h for hours, and then as type float at the end to convert them to floats. But this isn't necessary unless you have a good reason to do so. So now we have our xarray object that has some dimensions and coordinate variables. Now we need to add some data variables. So we can do that. let's imagine we have some chlorophyll A values, and we have some list of values. This is 5 points, 1 for each of the depths. Then we can go to where we're creating our xarray object, and we can add a comma, and we can write data vars equals, and another dictionary. Call our variable whatever we like, chlorophyll A perhaps. And then now we need to open some round brackets. We need to say which dimension this data variable has. So that's going to be depth in this case. And we're going to write our name of our object, our variable that we've created, chlorophyll A here. If we run that, what we can see is we now have a data variable, chlorophyll A. It has a dimension of depth. These are floats, and our values are here. So what if we have a data variable that has more than one dimension? We can imagine we have an object like wind speed. And what I'm going to create here is a 2D NumPy array of random values. So I'm going to go numpy.random.randint. The values are going to be ranging between 0 and 10. And we can put size equals 3 by 3. So we're going to have one value for each of the latitude and longitude pairs. Let's just have a look at how that looks. And we will comment this out again and hit play. In the terminal, you can see this 2-dimensional array. So now let's add this to our xarray object. And it's exactly the same. We can just create another key value pair under the data variables. We can call it wind speed. In this case, we want to give a list of different dimensions. So we have already a latitude dimension and a longitude dimension. And we make that equal to wind speed, our variable. And there we go. Our data variable wind speed has 2 dimensions, and here they are. In this display, this looks like a 1-dimensional array. I can assure you that it's not. If you want more proof, you can just print the values back. So wind speed, and then dot values. And there you go. And this ability to store data in multidimensional arrays is actually a big advantage of NetCDF over tabular data formats like CSV, for example, where you're restricted really to having data in a single dimension. In this case, the data are ready straight away to use as a multidimensional array. You need to be a little bit careful sometimes in which order you're writing these dimensions. Let's imagine that we actually only have 2 values of latitude. This is therefore a 2 by 3 array, and we have latitude and longitude written here. Let's see. That's been created okay. But if, for example, we had written our dimensions in the wrong order, like this, you see that we do get an error message that is very clear and tells us that there's conflicting sizes for the dimensions. But in case you have an example where you have 2 dimensions of the same length, you just need to make sure that you've been consistent in the order that you're referring to the dimensions. So here, latitude, longitude, latitude, longitude. It's a 2 by 3 array, not a 3 by 2 array. Adding 3-dimensional data is no different. We can just add a 3-dimensional NumPy array here. Again, we're going to do numpy.random.randint because I don't have any real values. They're going to range between 20 and 30 in this case. And the size is going to be equal to, let me check, we'll do latitude 2, longitude 3, and depths 5. No, let's instead just derive that. We can do len latitude, len longitude, and len depths, where len is length. We can create another key value pair where we have a value called temperature, and that is equal to in round brackets, our dimensions, latitude first, then longitude, and then depth without the S, and our three-dimensional NumPy array, temperature. And there you go. Now, I expect that some of you watching don't have your data in some multidimensional array. You might have your data in a table. So how can we convert our data from some tabular format, perhaps in a pandas data frame, into a multidimensional array? So I'm going to copy in some code here that I created earlier. And I'll go through this really quickly because it's not too important. It's just how I'm creating a pandas data frame. You can probably just load yours in from a table. But just in case you're interested, I'm creating some empty lists. I'm looping through each of my variables, which I have here. So there's going to be 5 times 2 times 3 iterations. So 30 iterations. And for every iteration, I'm appending what the depth value is, the latitude value, the longitude, creating a salinity value and appending that. I'm adding all of those values, all of those new lists, to a data dictionary, and I'm converting that into a pandas data frame. Which reminds me, I also need to import pandas as PD. So let's comment all of this out again. Now we'll run this, and you have your data here. So maybe you have some data that looks something like this. So what you can do is you can then create your salinity three-dimensional array. And NumPy has this neat feature where you can go NumPy array. You can take your salinity column from your data frame and you can reshape it into a multidimensional array. The order here is important. This should be the sort order of your data frame. So this data frame is sorted first in order of depth, which has 5 different values. Then in order of latitude, which has 2 different values, and then in order of longitude, which has 3 values. Let's have a look at that three-dimensional array. And I've made a mistake here. Yep, I see what I've done wrong. You first need to create your NumPy array, and then you need to reshape it. So just this code will create a one-dimensional array. Then you need to reshape your one-dimensional array into 3 dimensions of these lengths. Let's try that. And here we go. Again, if you like, you can also replace this with len. It was depth first, wasn't it? Then len latitude and len longitude, which will be more helpful if you don't want to count how long your different arrays are. So now let's write those to our xarray object. We can get rid of these prints again. And we can uncomment this. And we can do salinity, round brackets. We need to remember this order. So this is going to be depth, latitude, longitude in this case. And our array is called salinity, oops, not saturation. And our array is called salinity 3D array. If you do get this order wrong, as long as the dimensions are different lengths, it will complain and you can rearrange as you need to. So there you go. But is that compliant with the FAIR principles? No, it's not. We need metadata. So let's create another section here. Metadata. So we can have global attributes. These are metadata that describe the file as a whole. So this could be, for example, xrds.attributes, title, and some title for the dataset. And then you also have variable attributes, then you just do, you call your variable. So let's say time, and then attributes units to go back to one we gave earlier. And we'll remember that this is seconds since. And then we can copy this start time, if this is what we've used. Double quoting here. Then we're going to add a Z, which indicates that this is UTC time. So in CF-NetCDF, your times should really be in ISO 8601 format. So this is an international standard. And there's some examples here of how you can input data of different precisions and for different time zones. It doesn't really matter if you use UTC time or you use the local time zone. I guess it depends on the data. Maybe you want to show some diurnal variation and therefore you might want to use a local time zone. As long as you're specifying it in the units, it doesn't matter. But how do we know which attributes to include? Well, this is where our conventions come in. So if you remember, we have the CF conventions, that's climate and forecast. And we also have the ACDD convention, that's the attribute convention for data discovery. So I'll put these links in the description. This is the home page of the CF conventions. There's different versions that are released from time to time. We're going to look at the latest version. And this is a really long document, a few hundred pages. Now, you don't have to read all of this, of course, but you can think of this like a one-stop shop with all the information you need on how to encode different types of data. So let's say, for example, you have some data with a latitude coordinate. You can read this and it tells you some information about what attributes you should be including. The same for longitude coordinates, vertical coordinates, whatever. If we go to the top, there's also a lot of different sections that you can read through. We have data that are representative of cells. So if, for example, you have a data point that is representative of not a discrete location, but instead is, for example, the average over some coordinate range or some temporal range, then you can think of that data as being representative of a cell. I'm going to go through this later in this series, so I'll just point out that this is there for now. And there's all different types of examples for different types of data. So if you scroll down to the appendix, you can see all sorts of different examples. So how I use this document is just finding the relevant sections to me, or just scanning through it with Find. What we're talking about now, however, is metadata. So there is a section here, Appendix A, where it discusses attributes. And here there's a list of all the different attributes that you can include in a NetCDF file. There's quite a lot. And it tells you here, under use, whether they are for coordinate variables, dimensions, global attributes, and many of the attributes are valid as both global attributes and also variable attributes. I'll discuss which ones are required and useful back in Python, and some of these other attributes I will discuss in other videos. But of course, feel free to scan through if you like. Now, unfortunately, the CF conventions are rather light when it comes down to global attributes or discovery metadata. So discovery metadata is metadata that helps someone discover or find the dataset. And this is where we also use the ACDD conventions. So ACDD conventions, we're looking for this one. And what this is just a list of global attributes that you can include in the file. Some are highly recommended, and also suggested below. And also there are some highly recommended variable attributes. The three of these are taken from the CF conventions, but the coverage content type is just from ACDD. Actually, it's an ISO 19115.1 code. So you just include one of these as your value. Now, back to the global attributes. These are good recommendations, but if you want consistency between datasets, It's really more effective if you have requirements. So I work at the Meteorological Institute in Norway, and we have certain requirements for global attributes if you're creating a NetCDF file that you're going to publish with us. These attributes are all taken from the ACDD global attributes, but the benefit here is that we've told you whether they are required for data submitted to our catalogue. And of course, you don't need to follow these requirements if you're publishing your data elsewhere, but they are sensible requirements. So if you're wondering which attributes you should be including or which are less important, this is a good place for you to look. There are some other global attributes that you can include that are not part of ACDD. Feature type is actually a part of the CF conventions. And there are some other attributes that you can include, like the ISO topic category, activity type. So if you imagine you're on a data portal and you want to filter through a load of data sets, these are perhaps some useful things that you might want to include to help people do that. And you can include any custom attributes that you like on top of the requirements. You don't have to only use these attributes, but any attributes you include on top should be as well as these attributes, not instead of. So back to Python, I'm going to get rid of this for now. We're going to start with some variable attributes because there's less of those. So let's call one of our variables. Let's start with latitude dot attributes, and this is equal to a dictionary. And we can use key value pairs for all of our variable attributes. So we have standard name, and this is a standardized name for your attribute. So you can't just write whatever you like here. If we go back to the CF conventions page, we have this table of standard names. So you can look through here, but there's a lot. So perhaps most useful is to use this search bar. We have data with latitude. You can open this up and read the description, and you can include this name in your standard name attribute. So these standard names are a controlled vocabulary of terms. It means that everyone who's encoding data with a latitude coordinate should include a standard name of latitude, spelled exactly like this. So this is standardized, here is not standardized. You could equally have called it latitude with a capital L, for example, or lat, or whatever. But if you want to be able to automate processes, you need some form of standardization. So we have a standard name attribute here. The other advantage of this is the descriptions that you have. Now for latitude, this is quite obvious, but if we exit the search and show all the names again, it might be less obvious to you what some of these other standard names are. So if you were to see some data with a standard name like this, you can come through and read this description, and you can understand what is meant by those data. And you would hope that the data creator, you in this video, has also read this description for the standard name. And therefore you, the data creator, and the data user should have some common understanding of what those data are. This of course also makes it machine readable, which makes it fair. If you're not using standard names, your data aren't fair. You also have the canonical units. In this case it's seconds. You don't have to use exactly these units, but you should be using units that are physically equivalent. So you could, instead of seconds, use hours or days, but you couldn't use meters, for example. As well as that, another required attribute is the long name. Now, whilst this is your standardized name, the long name can be whatever description you want to give for the data. So, description in your own words. For latitude, this is quite self-explanatory. You can just write this if you like. Units. This should again be standardized. This, in this case, is going to be degrees north. But we can see this in the relevant section of the CF conventions documentation. And then we're going to have this coverage content type. You might recall we saw this on the ACDD conventions page. We go to the bottom, highly recommended variable attributes. And so in this case, we're just going to use coordinates. Our data variables later are going to be physical measurements, but this could also be model results. That's a good reminder that if you're working with model data, you can also include these in a NetCDF file. So let's run that. In the display in the terminal, you don't actually see these variable attributes, but you can if you print instead the variable. And there you go. We're going to do some copying and pasting now, because longitude is next. That, of course, is going to be very similar. And we have some more to add. I'm going to fill all these in really quickly and go through them. There's no need for you to watch me fill all this out. So for depth, we have the same for attributes. We have this additional attribute positive with a value of down, which we've taken from this section of the CF conventions. We have time below, the units, seconds since the start time, as we mentioned earlier. And this time we've added an attribute calendar with a value of standard. And you can see this described in this section, where you have different values you can use. I guess in most cases it will be standard. Our data variables, in each case we have the same for variable attributes. Our coverage content type is physical measurement, and the standard name has been taken from the CF standard name list. So that's it for the variable attributes. We can now go on to global attributes. Again, we can add these one by one, like xrds.attributes title equals my title, for example. Or we can add them all together as a dictionary. So I'm going to copy and paste a load of information into here. And I'll describe some of these that are more important. At the top, we have the ID. So this is an identifier for the dataset. You might already have one. You could also use the DOI of the dataset or some other universally unique ID. The naming authority below that is whoever provided that ID. The summary is analogous to the abstract of a paper. The creator, now this is not just the person creating the file. The creator is the person or people responsible for creating and collecting the data. So you can think of this as anyone who might be an author for that dataset. The creator type is either going to be person or group, institution or position. It'll be assumed to be person if it's not mentioned, but best to include it. And you have their institution, name, email, and URL. Now, in this example, there are two different creators, myself and John Smith. I've included them with a semicolon separated list. I've then also included the email for every single person and the institution. The URL, it's best practice to use the ORC ID. So people change institutions, URLs change, but the ORC ID will be fixed through time. So, for example, this is mine. If you don't have one, I really recommend that you get one. And you just copy and paste this ID here. Now, in this case, John Smith doesn't have an ORC ID. So what I've done is I've left it blank for him, then added the semicolon, and then added the URL. Now, the problem is if I had done this, which I often see, it's not clear whether this URL relates to John Smith or myself, or both of us. So each of these attributes should be semicolon separated lists, and all of those lists should be exactly the same length, regardless of whether there are applicable values or not. And that's the same for the institution. So if they were both at the same institution, just put the institution twice. We then have the time coverage start and end. Again, this should be in ISO 8601 format. The start and end time that the data have been collected. For keywords and keywords vocabulary, again, we're going to use a controlled vocabulary. In this case, I've used this, and you should copy this exactly if you're using the climate and forecast standard names. And you just copy all of the standard names that you've used in the file here. You might say that this is unnecessary if you have already included standard names in your variable attributes, but this is just how it is at the moment and you should follow that convention. CF standard names aren't the only types of keywords you can use. You can also use the GCMD keywords if you like as well. The GCMD keywords are here. This stands for the Global Change Master Directory, and you can look through and find a relevant keyword for yourself, or you can search for it here. In this case, you have to include the whole path to that keyword. So for example, if you have these sulfur oxides, you would need to write all of this. I think the CF standard names are easier to work for as keywords, that's why I've shown this in my example. The institution is the institution primarily responsible for the data. The publisher is the details of the data center where your data will be published. For a license, the most common license you will see used is the CC BY license. This means that your data are free to use and adapt, but only if they are properly crediting you. The other license you might see used quite often is a CC BY NC license, which means that your data should not be used for commercial use. But I would kind of advise against this unless you have a really good reason. Commercial use can be a wide range of things and not all commercial endeavors are bad. For example, someone's doing some science communication in some commercial journal. This would restrict them from using that data. So use CC BY 4.0 unless you have a good reason to use the non-commercial. Conventions. This is perhaps the most important global attribute. This describes which conventions you've followed in the file. And ideally, you should be testing your file against those conventions. So here we just included a comma-separated list, ACDD-1.3 space CF-1.8. And I will show you how to test your file against those very shortly. Now, there are some attributes that are required or highly recommended that I haven't included here. And that's because it's sometimes easier to derive some of the global attributes within your code. So let's do that. Let's say we have xrds.attributes geospatial lat min. So this is the minimum latitude you'll find in the data. Well, we already have that. So we can do min xrds latitude dot values. If we run this, this is the first time we're seeing the attributes in the file. We can see all the attributes we've added here, or actually just 12 out of 21. But we can see the geospatial lat min has been displayed. If we do want to see all of the attributes, we could do that, just print like this instead. We can do the same for the maximum latitude and the minimum and maximum longitude. And this is creating a bounding box for your data. Another attribute we need to include is the time that the file has been created. And for that, we're going to use a different library. We need to do from datetime, import datetime as dt. And back down here, let's get the datetime now is equal to dt.utc now. This will give you a datetime object, but we want a string in a certain format, so we can go .strf time, string format time. You can see that VS Code has given me some examples of how to do this. So we have year dash month dash day. Then I'm going to use a T, and then we have hour, minute, second, and a Z to show this is UTC time. So we can now add an attribute called date created, which is another required attribute, equals dt now. And finally, another required attribute is history. So this is an audit trail for modifications to the data. So if you're updating the data through time, you should have one line in this attribute for every time you've updated the data. So you can do something like file created at, and to include this dt now within the string, you can make this an f string, which means you can include your variable here, dt now, using xarray in Python by Luke Marsden. And that's all the attributes I'm going to include in this case. Now you want to export your data instead of print it. We can just do xrds.toNetCDF, and we can give either the file name or maybe the whole file path to our NetCDF file we want to write. So I'm going to call this for the fourth video in this series, example multidimensional file.nc. And that will actually be fine. Now, in some cases, we might want to actually specify the encoding. So this is useful if you want to specify how certain variables will be compressed and what data type you want them to be stored as. Otherwise, it will just assume. So we can do that here with encoding equals my encoding. And of course, we need to create this my encoding object. And I'm going to copy and paste one I created earlier. So my encoding is again a dictionary, and each key within that dictionary is one of our variables. Now this dictionary is a nested dictionary. So for depth, we have another dictionary, where the key value pair now is how we're encoding our data. So we've used dtype here to say that we want our data to be stored in int32 format. That's 32-bit integers. And we've done this special attribute here, underscore fill value, and that's going to be none. That's because coordinate variables shouldn't have any fill values. But what is a fill value? Well, this might be assigned to our data variables, and this is some exceptionally large value that will show up as a spike in the data usually. And this value will be used to fill in any gaps that you have in the data, so anywhere that you don't have a number. So for this example, for your chlorophyll A variable, for every point where you didn't collect data or there isn't a value for some reason, this value will be filled in place. And most softwares are now intelligent enough so that someone reading in the data later won't actually see these values. They'll be replaced again by empty spaces when you load the data in. We then have this zlib. This is to specify whether you want your data to be compressed. So we've just included false. And we've done the same for all of our different variables. I've made a typo here, but I can run this again. And another typo, my encoding with an underscore, and there we go. And we can see on the left-hand side, this file has been created. So now let's run this file for a compliance checker. So I'm going to use this compliance checker here, the Integrated Ocean Observing System compliance checker. And you can run it through ACDD 1.3, CF 1.8. You can add your file, and let's hit submit. It says that there are no errors. That's good. There are some warnings that we might want to go and address. Let's read this. This is telling us that ideally our dimension should be in time, vertical Y, Z order. But this is just a warning. I mean, ideally you should fix this, but your data is compliant with the CF 1.8. So you can go fix this if you like. If we hit back, we have to upload our file again. And we run this time through the ACDD conventions. Again, highly recommended, all checks passed. There are some recommended attributes that I haven't included, but again, these are recommended and not required. Some of them, for example, time coverage duration, are not really adding anything if you already have time coverage start and time coverage end. But please take heed of these recommendations. You might scan through here and find some attributes that are useful that you might decide you want to add. So that's everything for this video. If you found it useful, hit the like button, and please consider leaving me a comment. I do read them and it does make me happy when someone has found my video useful. Equally, if there's something that wasn't clear, you can let me know. I might respond in the comments, or if it's a big and interesting topic, I might consider creating another video. So I hope you'll join me for the next video in this series, where I'll be explaining how you can structure your NetCDF file, or whether you should be creating more than one file for your data. I'll be going through what the best practices are, where it perhaps isn't obvious how you should structure your data. So see you next time.